So firstly, I will start with the background of the study. So what is a COVID-19? COVID-19 is an infectious disease caused by a newly discovered strain of coronavirus, a type of virus known to cause respiratory infections in humans, which infecting the people in Wuhan province. The coronavirus diseases COVID-19 was identified as the causative virus by the Chinese authorities on the 7th January. Before 11 March of 2020, the World Health Organization (WHO) declared that this coronavirus as epidemic, but then after 2 months, they upgraded it from epidemic to pandemic, which means it has affecting the whole world. Since it has affecting the whole world, Malaysia is not exempted from these diseases. The first cases of COVID-19 in Malaysia was detected on 24th January of 2020. This case became more worse with the existence of public cluster that sparks the spread of this disease. So, due to the rapid increase of these diseases, the government had launched the Movement Control Order (MCO) starting on 18th of March 2020 as an initiative to curb the spread of this disease. So next, I will present about the problem statement of this study. So as we know, COVID-19 has become a worldwide phenomenon as it evolved from epidemic to pandemic because it is affecting the whole world. So in Malaysia, the first case started to be detected on the 24th of January 2020. It came from a travelers from China who came to Malaysia without knowing that they are the carrier of this disease. And then this disease has becoming more worse as the public clusters start to exist and other clusters also start to exist. So in order to curb this problem or these diseases, the government has done an initiative which is they enforce an MCO and during the second wave of the virus spread in order to reduce the spread of these diseases. Therefore, we wish to study a COVID-19 of Malaysia during the second wave after the MCO being established, where we assume less people get infected during this phase. Next, for our scope of study, we are choosing Malaysia as our scope because we are Malaysian and Malaysia is our homeland, and also the number of articles or research that had been done in Malaysia about COVID-19 is only a few or small, so we decided to study the COVID-19 in Malaysia only. So the main objective of the study is to model the development of COVID-19 in Malaysia during the Movement Control Order (MCO) period from 18 March of 2020 until 28 April of 2020, which can be achieved by the following sub-objective, which is first is to approximate the trend of COVID-19 infection and recovery among the public during the Movement Control Order using SIR model. Second, to compare the approximated trend of COVID-19 infection and recovery with the actual trend of infection and recovery during Movement Control Order. And lastly is to examine the accuracy and precision of SIR model by using the error analysis approach. For the significance of this study, we hope that this study will help the Malaysians to have awareness about this issue and help the country to flatten the curve by adhering to the MCO. And the result from this research also is valuable to the mathematical practitioners in developing a better practice and tools for mathematical study of infectious disease. Next is the mathematical model development. For this part, we only consider the duration from the first phase of MCO until the third phase of MCO. So firstly, to develop the mathematical model of SIR model, first we list all the differential equation for susceptible, infected, and recovered as follows. As you can see in the equation 1, 2, and 3, which is equation 1 is a susceptible equation, equation 2 is a infected equation, and equation 3 is the recovered equation. From the equation, beta is the number of infections that produce a contact, while 1 over gamma is the infection period. In a closed population, the total population N consists of number of susceptible, number of recovered, and number of infected, which satisfy the equation of 4, which is St plus It plus Rt equal to N. And next, for equation 1, 2, 3, and 4, we divide it by N on both left hand side and right hand side. Then all the equations will become as follows. As we can see in equation 5 is the SR S0 ST S, which is a small s, and the equation 6 is a small I, and equation 7 is a small r, while for equation 8 is the St plus It plus Rt equal to 1, since N divided by N is equal to 1. And then the initial value is selected such that S0 equal to S0 plus I0 plus R0 equal to 1. In this study, we are having a problem to solve the equation 5 and 6 because the value of beta is not readily available for the COVID-19 diseases. On the other hand, beta is related to the basic reproduction number, which is given by R naught equal to beta over gamma. We can express this beta in terms of R naught and gamma, and we will get beta equal to gamma times R naught. And then we substitute this equation 9 into equation 5 and 6, and we will get equation 10 and 11. So in order to approximate this model, we have made a few assumptions when we use the fourth order Runge-Kutta method to model the trend of COVID-19 infection and recovery among the public during the movement control order. These assumptions are essentially conditions that should be met before we draw inferences regarding the model estimated before we use a model to make a prediction. So the first assumption is this is an epidemic model, so we will not consider the number of births and deaths, so it is not included in this model. And next, we consider the people who are recovered will not get infected again. The third one, we reduce the total population and use a small population, which is equal to 1,000 people, to get a more accurate, more precise trend of infection and recovery. And lastly, we consider only the active cases for the infection graph, while for the recovery graph, we use the cumulative number of recovery.
For our study, we will use fourth-order Runge-Kutta method to solve the differential equation of SIR model. The reproduction rate for COVID-19 that is estimated by WHO is between 2 and 2.5. Meanwhile, Health Ministry of Malaysia has reported that the reproduction rate of COVID-19 in Malaysia was to be 3.55, which is that before the MCO was enforced. According to WHO, the average recovery time for mild cases can take up to 2 weeks to recover, while for severe or critical case, it can take up to 3 to 6 weeks for the patient to recover. For the population, there are 32,730,000 people in Malaysia as per first quarter 2020. But as mentioned before in the assumption, we will use the total population equal to 1,000 people. In order to determine the SIR model, we will use the real data of infection and recovery for the first day of MCO as the initial value. Therefore, our initial value for the population variables are S, which is susceptible, equal with 872, which is 1000 minus 117, which is infected, minus with recovery 11, divide by the population, which is 1000, and then the number of infected people is 117, which is the real data, and R, which is recovery, is 11, which is also from the real data. So in terms of scale variables, these initial conditions are S0 equal to 0.872, I equal to 0.117, and R equal to 0.011. We summarize it into a table which there are population, reproduction rate, and infection period. For the population, as we have seen before, we use a smaller population to increase the trans accuracy, which is with 1000 people. And then next is reproduction rate, which is the average number of people that can get infected by an infected person. We use R naught equal to 3.55. This is the reproduction rate that is reported by the health minister before the enforcement of MCO. And then the infection period by day, which is the number of days of an infected person takes to recover, is 1 over delta equal to 21 days. This value refers to WHO data that is best matched to the trend in Malaysia.
Okay, here is the combination of two graphs that has been computed, which are infection and recovery group. This graph was generated by using Wolfram Mathematica 8.0. We can observe, here we can observe the approximated trend of infection and recovery of COVID-19 in Malaysia during MCO based on the graph. The x-axis of the graph is the number of days of MCO, while the y-axis is the number of people who are infected and recovered. The blue line is the number of infected people of COVID-19, with 117 people are infected just as on first day of the MCO. For the infection group, we consider it as the active cases only, where we terminate the number of cumulative recovered from the number of cumulative infected. As we can see, the infected line graph rose smoothly and reached its peaks around day 24 with around 389 people are infected, then slowly decreased to around 276 people where they are still infected by day 42, which is the end of MCO3. On the other hand, red line shows the cumulative number of people recovered from COVID-19 throughout MCO1 to MCO3. The total number of people recovered from COVID-19 at the beginning of the studies was 11 people, which is obtained from the Ministry of Health in Malaysia's website on the first day of the MCO. The line graph is increasing slowly over the time until the end of MCO, which is day 42, and around day 27, the infected line crossed against the recovery line, which shows that the number of people recovered are higher than infected. However, this graph shows no sign that the total population will fully recover from COVID-19 in the near future, and it is expected to take a long time to die out since there are still a number of people infected. And approximately 62.6% of the population have recovered from the infection, which is around 626 people on day 42 of MCO.
Here is the comparison trend of COVID-19 between the approximate model and the real data from the first phase of MCO until the third phase of MCO. The graph is showing the distribution of COVID-19 cases in Malaysia, which is the real data. The red line is the active cases of infected, and the blue line is the cumulative recovered. Well, according to the graph, during the first phase of MCO, the active cases of the infected line graph increases from day 0 until day 14, which is also the same with the trend of infected line of the approximated model, while the cumulative recovery line shows a slow increase during this phase, which is the same with trend of recovered line in the approximated model. This happens because in the early MCO, the Malaysian is reluctant to stay at home and keeps going out spreading the virus, ignoring the government's regulations. Then in the second phase of MCO, the line of active infected case keeps increasing until it's achieved its peak at day 19 and started to decrease at the day after. This is contrasting a little bit compared to the trend of the other approximated model, where the line of infected increases and achieves its peak at day 24, which is differ a few days. During the second phase, the number of infected showing a big increase trend as there are numerous people who are getting infected with the virus and creating more clusters of infection. In order to overcome this problem, the government started using their security forces such as PDRM and ATM to make the people obey the rule of MCO. On the other hand, the cumulative recovery is showing a rapid increase during this phase, which is similar to the recovered in the approximated model, and during day 25, the recovered line intersects with active infected cases line, which is quite similar to the approximated model. While during the third phase, the trends of active infected cases keeps decreasing until day 42 for both the real data and the approximated model. This portrays that the Malaysian finally realized the importance of staying home and have an awareness of this virus. The recovered trend in the model is keep increasing throughout the time frame, which means that most of the infected people has been recovered from this disease. This is proven that the initiative taken by the government has succeeded to reduce the number of cases and flatten the curve. We can conclude that the approximated model is nearly similar to the neural trend of COVID-19 during MCO. Therefore, the model may be varied slightly compared to the real data, as there are more factors that influence the real world situation compared to the model which only consider a few assumptions. Here we run the error analysis to analyze the inaccuracy and imprecision of the model by using the SPSS to compute the calculations. On the table, we get the statistics values such as mean, standard error, skewness, and courtesies for the infected and recovered model. And for average mean for infection and recovery group, which are 0.0123 and 0.0204, is very close to the zero, which shows a high accuracy of the model for both the infection and the recovery group. While the furthest skewness of the error for the infected is negative 0.957 and recovered is 0.168, where all these values are between negative 1 and 1. This is indicating that the error value is normal and acceptable. Lastly, the courtesies value for infection and recovery, illustrating that the data are normal because the courtesies value for infection and recovery are negative 1.55 and negative 1.365, which are in between negative 12 and 12. As a conclusion, this coronavirus has evolved into a pandemic where it is affecting the whole world, including Malaysia. The virus spread in Malaysia is becoming more serious as more people are being infected during the second wave. In order to model the development of COVID-19 in Malaysia during the movement control order period, we make a few assumptions under SIR epidemic model along with the fourth order Runge-Kutta method to solve the differential equation of SIR model. Based on the results, we succeeded to approximate the trend of COVID-19 infection and recovery among the public during the MCO using SIR model. From the comparison between the approximation model and the actual data, we found that both infection and recovery trend is quite similar. Meanwhile, the error value for the approximated model is quite low and considered normal.
Okay, lastly, our limitation in this study is there are no incubation period for COVID-19 in our assumption. Then we assume that every person that have been infected with COVID-19 will not get infected again in future. And then we also use infection rate and reproduction rate in order to produce the approximation of transmission rate beta instead of using the real value, because we lack data of the transmission rate. Therefore, we recommend for future study to use SEIRS model, as people who are recovered from COVID-19 might return to the susceptible state and use beta to get a more accurate result with the real data. Moreover, it is also better for future study to include the incubation period, death, and birth to study the development of COVID-19 in Malaysia.